So to make a comparison with the WKB wave function, we will take this term negative because in WKB we will be writing integral from x1 to x for region 1. So how to negate this power term as well as this power term. So this will be getting modified as positive. That term is taken first, theta plus 1 by 4 theta. This power limits of integration are altered so that this minus term becomes plus e raised to I by h cross integral x1 to x pd x prime. And from this term, let me take minus I outside. Minus I into what remains is theta minus 1 by 4 theta into e raised to minus I by h cross integral x1 to x pd x prime. This limit of integration is also negated. Now we make a comparison of this wave function that we have formulated on the basis of connection formulae with the WKB wave function in region 1. So the coefficient of e raised to I by h cross integral x1 to x p dx prime is a1 by root p. We can omit root p, so this is a1. And that of this negative power term is b1. We have obtained phi 1 using connection formulae, say this one. So the coefficient of this positive exponent term happens to be theta into 1 theta plus 1 by 4 theta into a3. So this should be identical with a1, so that we can take this as say equal to a1, and this parameter must be equal to b1. a3 into this parameter must be equal to b1. a3 is outside the common curly bracket. That is being taken here. a1 equal to theta plus 1 by 4 theta into a3, and b1 equal to minus I into theta minus 1 by 4 theta into a3. This minus I coefficient is an indication of the phase change upon reflection, or is an indicative of reflection, as this is an exactly similar derivation you might have met in first semester while you talked about the reflection of electromagnetic radiation at a lossy medium, or at the interface of two media, while you talked the electrodynamics. So the transmission probability or transmission coefficient T, as we have already obtained, is a3 by a1 whole square. So I'll have to put a1 to the right side and this coefficient is taken to the left side. What remains is a3 by a1 on the right side, and I'll have to square it. Then that will be equal to 1 by theta plus 1 by 4 theta whole square. That is theta plus 1 by 4 theta whole raised to minus 2. Since this quantity is in the denominator, the parameter, the contribution of this quantity is much smaller comparing with this parameter. So approximately this can be taken to be say 1 by theta square, or theta power minus 2. And I hope you recall theta, that's equal to integral from x1 to x2. Of course e power is there, exponential power integral from x1 to x2 p dx prime, p dx prime. So square of this one with a minus power is, this power term will have say minus 2. That is, transmission probability for tunneling is e raised to minus 2 by h cross integral x1 to x2 p dx prime. See, this is a decreasing exponential parameter. So the transmission probability will be falling exponentially, very rapidly, with two different quantities that include or that decide the momentum parameter. The momentum, as you know, is given by root of 2m into e minus v. 2m into e minus v. As the momentum parameter increases, the transmission probability decreases. There are two choices for the momentum parameter to increase. First one, that is, say E minus V is the parameter. When V is much larger, that is height of the potential barrier is very large, then E minus V will be very large, that is momentum will be very large. Under such a situation, transmission probability will be infinitesimally smaller. Another parameter that decides the transmission probability is integral over dx. The dx is the thickness from x1 to x2. If this quantity increases, x1 to x2 range increases, then also this integrand increases. That also account for a rapidly falling transmission probability. So we conclude transmission probability falls exponentially with first one, height of the potential barrier, number two, width of the potential barrier from x1 to x2. So these are the two parameters that control the transmission probability for tunneling. And I have already told you, if you are interested, you can evaluate the reflection coefficient, which is B1 by A1 whole square. B1 by A1 can be obtained by dividing this equation by this equation. B1 by A1 will be there on the left side, and on the right side A3 vanishes. What remains is minus I into theta minus 1 by 4 theta by theta plus 1 by 4 theta whole square. That is theta minus 1 by 4 theta whole square by theta plus 1 by 4 theta whole square. We are not going to simplify it. Of course, it is of the form A minus B whole square by A plus B whole square. And if you sum up this is also a wonderful result that also may be asked for proving as long as your examination is concerned. The sum of transmission and reflection coefficients will be equal to 1. This is something that you have also discussed in electrodynamics as well. The sum of transmission and reflection coefficients will be sum of, say, this one with this one. So they have a common denominator, that is theta plus 1 by 4 theta whole square. So their numerators are to be added. 1 plus theta minus 1 by 4 theta whole square whole divided by common denominator theta plus 1 by 4 theta whole square. Now this is of the form A minus B whole square plus 1. Here A minus B whole square is theta square plus 1 by 4 theta whole square. A square plus B square terms are theta square plus 1 by 4 theta whole square. A square plus B square. Now you have minus 2AB, that is minus 2 into A is theta and B is 1 by 4 theta. Theta vanishes. You have 2 and 4 making it, say, 2 in the denominator. Now this is A square plus B square minus 2 plus 1 is here. A square plus B square minus half plus 1 is here. That is A square plus B square plus 1 minus half, that is, say, plus half. But we have seen that 2AB is equal to plus half. 2AB is equal to half. So that now this is of the form A square plus B square plus 2AB. That is nothing other than A plus B whole square. That is theta plus 1 by 4 theta whole square. So the numerator and denominator vanishes. You will get this, say, equal to 1. With that, we come to an end for the discussion on WKB approximation. In the examination point of view, this module, or say this portion of the module, is very important. You can have surely you can have 3 questions from this module, or say from WKB approximation, and one of these will be a short answer. Most likely short answer is criteria for the validity of WKB approximation. The second possible question is describe the principle of WKB approximation, and a third possible question in short answer section is describe the Bohr-Sommerfeld quantization principle. Most likely choice for essay is obtain the general expression for energy eigenvalue of a bound system, explain its significance. That is the derivation of Bohr-Sommerfeld quantization principle along with a supplementary problem. Either that could be the case of a linear harmonic oscillator or hydrogen atom. And generally you can have a problem that will be most often an application of the Bohr-Sommerfeld quantization principle. So make your preparations about this approximation procedure very well. In the next video we'll move on to the approximation method, the one and only approximation method that we will have to talk about as long as time dependent problems are concerned, that is time dependent perturbation theory.